Hey, hope everybody's doing well. In this related rate problem, I want to talk about a person walking away from a light pole and looking at their shadow. How does their shadow relate to the speed of their walking? So here's a specific problem. Suppose I have a person who's 5'6" tall, and they're moving away from a light pole at 2 feet per second. I want to know how fast the length of the shadow is moving, and also how fast the tip of the shadow is moving. In other words, the shadow that's created by the top of the person's head. And one of the things we're going to assume that this light pole is 12 feet tall. So, let's see if I can draw a picture here. That's my rendition of the ground, by the way. I have a light post. That should be straight line. Sorry about that. That's 12 feet. And I have a person that's going to cast a shadow. And they're going to be 5'6" tall. So that relates to, or that gets converted to 5.5 feet. And so what do I know about this? The person, they are moving away from the light pole at 2 feet per second. And, well, that's pretty much all I know at this point. Now, if I read questions A and B, I eventually want to put in a 25 in here. But for now, I know things are changing. So what do we know about this problem? Well, before we write down the know, just remember we have to label things. The distance between the base of the pole and the foot of the person, or the feet of the person. Let's label this with an X. Now let's label this part with an S. Well, this part right here, that's the shadow, because there is no light that gets over here. So this is all shadow right here. So what do we have here? It looks like we have two triangles. We have similar triangles. So there's lots of things that we know in this problem. So what about the calculus stuff? What about the rates? dx dt. Well, that's 2. What do we want to know? Well, we want, and this is a little bit more difficult, we want to know what ds dt is. That's the length of the shadow changing. That's part A. What about part B? Well, part B, we need to know this distance right here. Well, that distance is x plus s. So what we want is the derivative of x plus s with respect to time. Well, some rule tells us that this is the derivative of x with respect to t plus the derivative of s with respect to t. I already know this part. That's 2. So if I can figure out part A, part B is just adding 2. So let's try to figure all this out. So what's my big relationship here? Well, I mentioned similar triangles. So how do we do similar triangles? Well, we can look at 12 over 5.5 is equal to x plus s all over s. Big over the little is equal to the big over the little. Let's do a little bit of algebra here. So I'm going to kind of multiply this out, get rid of the fractions. I get 12s is equal to 5.5 x plus s, which I can rewrite this as 6.5s is equal to 5.5 x. I'm just going to subtract 5.5s from both sides. So this is my model. I think this is the easiest model that we've done so far. Let's take a derivative of this. I get 6.5 ds dt is equal to 5.5 dx dt. Well, I know what dx dt is. So I need to solve for ds dt in all of this. This is going to be 5.5 times 2 all over 6.5. And remember the units for this particular problem, since things are measured in feet and seconds. This is feet per second. So part A. My answer is 11 over 6.5 feet per second. Part B, well, is 11 over 6.5 plus 2, because that was my extra dx dt there. Feet per second. Now this, I think, is an amazing problem. Why do I think this is an amazing problem? I never used the 25 feet from the pole. Regardless of how far the person is away from the pole, this is always how much the shadow grows. And this is always how fast the tip of the shadow is moving. So if the person is walking at a constant rate, the length of the shadow and the tip of the shadow is also moving at a constant rate. I still think this is an amazing problem. I think I saw this over 30 years ago when I first took calculus. So I hope that was useful. If you have any questions, let me know. Have a great day. Bye.